welcome to the deep dive performance session on the University Day at Devoxx, and welcome to Devoxx. First up, we're going to have Jean-Philippe Bempel from Ulink, and he's going to be talking about lock-free programming, so that's going to be pretty cool. And then Nitzan, who's, wave your hand, fantastic. So Nitzan and I are then going to be talking about profiling, how profilers work, different profiling biases, fantastic stuff like that. And we also have a fourth speaker, Sergey, who's from Oracle. But unfortunately, just like Java 9, he's running behind schedule at the moment. So hopefully he will turn up in time. But if not, I'm sure we will. We can talk for hours and hours. Or we'll just get Kirk to talk for a bit. That'll be fantastic. Cool. But I'm sure he will turn up. Fingers crossed. Anyway, I will hand over to Jean-Philippe, who's going to talk about lock-free programming pro tips.
Okay, thank you, Richard, for the introduction. So welcome to this session about lock-free programming for this deep dive performance university. So my name is Jean-Philippe. So in advance, sorry for my French accent. Sorry. So I'm working at Ulink as performance architect, and my work is most of the time on low latency application. It means that the process is under 1 millisecond that we are measuring, and contention can show outliers, and it is important for us to shave them. So we apply time to time some lock-free techniques, and this is a way to achieve our goal. So in this session, the agenda will be to learn how to measure contention and what is contention. We'll explain the component swap technique. A slight introduction to the Java memory model, my approach at least, and some explanation about the disruptor and the ring buffer technique. And finally, with the ticketing technique, with the ordered scheduler in British. Anyway, and first, let's talk about immutability. To just put aside this topic for the rest of the session. So for immutability, it's it's easy to make something thread safe with immutability. So like functional languages or actors using it. But there is a cost in terms of performance, GC. So you pay back this by the GC if you are not running with Azul. Sorry. So if you are a structure, a shared structure with immutable object, and you have multiple threads that are reading, that's fine. But if you are modifying this structure a lot, you will allocate a lot. And if you have contention with multiple threads, you're allocating much more. So you're paying back with the GC cost here. So immutability is good, for at architecture design, but at code or class level performance-wise, it will be difficult. There is some technique that are used if you are some structure that are not very modify a lot, like the copy on write array list or some implementation of copy on write hash map that can be used, for example, for listener or whatever. But this is because this structure is not modify a lot, just rare. So that's why. So we are talking now on contention. So what is contention? Contention is when we have two or more threads that trying to acquire a lock. So all the other threads that try to acquire a lock are parking like cars, waiting that old lady cross the street. The only one thread that acquire the lock. So this is the main reason we want to reduce the contention, to improve the scalability of our application. So for contention, it's important to measure. don't guess, of course. But I would like also to add that measure, don't premature. We will learn some lock-free techniques, but don't apply it blindly without any measurement of what is your real bottleneck in your application and what is the real contention you have on your application. Don't try to go back home and say, okay, new stuff, new lock-free techniques, that's very cool. Let's apply this in all synchronized blocks we have on our application. So measure where is your bottleneck, where is your contention, and then to reduce this contention, you can apply some lock-free techniques. In a Java world, we have two kinds of locks, the synchronized blocks and the java.util.concurrent lock. To measure, for example, a synchronized block, we can use profilers like YourKit, JProfiler, ZVision from Azul. Usually those profilers use the JVM-TI API to get some information from the JVM. You implement it with native agent. There is some events that come from this API, like you're entering into a contended synchronized block, and you get some information for those to measure this contention. But by my experience, results are very difficult to exploit like this. I have an example on JProfiler. At Ulink, we are using YourKit, but this is pretty much the same. And here we have a toy example showing that we have some synchronized block. We have contention on it. We can see the monitor class here, but we don't have any call stack. So it's difficult to pinpoint where the synchronized block here. I'm not very familiar to JProfiler. Maybe I'm doing wrong, but out of the box, it's difficult to see where is my contended lock. Also, on the monitor class, hopefully I've typed my lock with a special class, but if I'm using new object on this lock, I will get the java.long.object. So without stack trace and the type of the object, very difficult to see where is my contended lock. On the other hand, we have ZVision. That's pretty nice. Maybe it's a little bit squeezed for you in the back, but they're very clean stack trace with counters getting how many synchronized block we have with the clean stack trace. So it's very easy to pinpoint where is my contended lock. So good to see and it's built in the JVM. So very good. For the other kind of lock, the java.util.concurrent.lock, JVM cannot help us here, basically because those implementation of lock are just regular classes from just like library JDK classes. But I found out that JProfiler can measure them, or YourKit is not able to. There is no option for this. But JProfiler can measure them. That's good, added value for this profiler. And I've also, preparing this talk, found that there is another tool created by IBM team called JProfiler, or Java Util Concurrent Profiler. And my guess about this, how it works, it's try to modify the Java Util Concurrent classes to instrument them for special implementation of reintroduce lock or read-write reintroduce lock, and reintroduce it in book ClassPass. I've also used this myself. I'll talk about this later. For JProfiler, for the reentrant lock, we have a nicer view. We have the instance of our kind of lock, reentrant read-write lock in this case, and we have a clean stack trace here, so it's easier to pinpoint the contented lock with this. So my way to measure contention before finding those tools is to get the JDK classes, the implementation, the source code, identify place where there is a contented lock, I mean the fail to acquire lock, put some just regular counters at this place. To identify the locks, I mean the location, I grab the call stack at the construction time into the constructor. I keep it in memory and logging regularly the status of the counter. I recompile it, this modified JD classes, and reintroduce in the boot class path. So it's cool for lab environment, but for production it's kind of difficult. But I mean, with this, we have a quantification of our contention. So we can have a benchmark on your application, measuring the contention we have and where it is, and then you can apply some reduction of this contention and see the difference in terms of quantity here. So it's measurable. Let's move on compare and swap. So compare and swap is basic primitive for any lock-free algorithms. It's used to implement blocks, like the reentrant lock or the synchronized block. They use this primitive. Or for any other synchronization primitive like mutex, semaphores, whatever. It's handled directly by the CPU in forms of instructions. So it can be very fast. So compare and swap basically is to update atomically memory location by another value if the previous value is the expected one. Whoa. This instruction takes 3 arguments, a memory address, an expected value, and a new value. So we have an example of this in assembly. Sorry, it's bleeding your eyes. So we have this value. This is the expected one, 2a, and 2b, the new value that we want to put in the location. Location is RBX, the address, and we exchange it. With the schema, it's like this. We have the address of the memory location and the expected value, I mean the current value in the memory. We have the expected value that we compare to this memory location, and then the new value that we want to atomically update and make sure that the previous value was this, and make this new value into this memory location. Going back to Java, we have access to this instruction indirectly. It is exposed in atomic access classes with the comparand set method. There is 2 parameters, expected value and the new one, and returns Boolean. The third argument is, in fact, the memory address is the field value inside a class. So we are changing the value of the field, that's the memory address that we have seen on the assembly level, with this. And if the exchange succeeds, the method returns true. Otherwise, it's false. an example of usage of this method is to implement the get and increment method. So we have two versions. The JDK 7 version, it's the basic algorithm. So we get the memory location, the current value of our field. We increment it, and then we apply the comparison set with the current value expected and the new one. If it succeeds, we return the previous value because it's get and increment. Otherwise, we're trying again until it succeeds. So if there is any like contention, but if there is another thread that tried to do the same, the comparison set will fail. And then we will try by rereading the value at the memory location to get the updated value, and then applying our increment here. For JDK 8, there is a slight optimization using the unsafe and get and add long with this. And this is recognized by the JIT compiler and specified like this. So it just get the increment, and we lock x add on the memory location with the increment. So we are leveraging the fact that the x86 instruction set providing this instruction to do this increment directly. It's much more faster than producing the same algorithm in assembly. How can we implement a lock with this primitive? Basically, the reentrant lock is implemented like this. We have a state integer volatile, and the lock method is just to complement set the state from 0 to 1. It means that we acquire the lock. State 1 say acquire the lock for the executing thread. If the CAS failed, it means that the lock is already acquired. So we may apply some, we park the thread, waiting that the lock is released, or trying again, whatever. And for unlock, it's just going back the state to 0. I mean, there is only one thread that have acquired this state, so we can safely put the state to 0 without any protection. Since JDK 6, synchronized blocks are also implementing this technique as a first try. They try to use the thin lock implementation that try to just compare and set states, and if there is any contention, they fall back to major inflating the lock. A practical example, an implementation of a lock-free algorithm is already inside the JDK, the concurrent linked queue. This is the simplest lock-free algorithm. Very simple. We'll describe it here. So we use the CAS, the comparison swap, or comparison set, whatever, to update the next pointer into to our linked list. If the CAS fails, it means there is a concurrent update in this queue, and we try again. We reread the new value, we move the next pointer to the right node, and we will try to insert this node with a CAS until it succeeds. So with an example, we have a queue with two elements, A and B, by a link queue. We try to insert concurrently two elements, C and D. And following this algorithm, we try to CAS. We are positioning on B, and we try to insert either C or D with the CAS. And in this case, one of the threads will succeed. This is guaranteed. So in this case, the C succeeds. and D fails. So for D, we're trying again. So we move the next pointer to C, and we try to do the cast again. It will succeed in this case because we have no other contention, other threads trying to insert into the queue. And that's it. Very simple. Now we are moving to a slight introduction to the Java memory model. This is just an introduction because if you want to go deeper into this model, I recommend to go to any other presentation made by Alexei Shipelev or the other presenter, Sergei Kuksenko, because there is more deep presenting about this. More theoretical for me. So my approach is more practical, so how it is really implemented by the JVM and how it works really. Interestingly, Java was the first language having this well-defined memory model in 1985. C++ get this memory model standardized in 2011. There is some issues until the JDK 5. Before that, there is some construction that was not behaving correctly because the JIT was optimized too aggressively, and there is no rule preventing some kind of optimization about this. But since that, it's pretty good. Let's get an example of what is going on with the JIT compiler and those rules. We have three fields in this class, A, B, and a field enable Boolean. And we have those three instructions here. For the two instructions, the two assignation to A and B, there is a data dependency. I mean, the A, the first one, the second one is depending on the first one. We read the A assigned before. But for the third instruction, enable, there is no dependency between the first two ones. In this case, the JIT compiler is able to reorder those instructions like this. For example, put enabled first, completely allowed to do this. In this case, if I have another thread that trying to execute this code, and if I want to make sure that we process an answer with the value 42, it can be difficult here. Because if there is reordering of enabled in first, I may process answer with 0. And I don't want to do this in my algorithm. So how to prevent this kind of reordering? Any guess? Good. I put volatile on enabled. And then I introduced memory barriers in my algorithm, materialized by the red line. So we have a red line here, memory barrier here for writing to the volatile enabled. It prevents to reordering the assignation on the enabled up. So A and B are already assigned before I unassign enabled. It's like committing on memory that we have all the assignation before that really happened before. And for reading the volatile enabled, there is also a read barrier here to prevent any other read to move up. So when I read enabled and I rely on the value from enabled, I make sure that when I read B, it is after reading the enabled. otherwise, the compiler can also read B before enabled without volatile keyword. Okay, maybe still too theoretical for you, but like someone says, the intention is the source code. The truth is in the ASM, proof in the pudding. So let's take an example of a class with 7 fields numbered and another Boolean field enabled. And let's do some, we executing the assign method 10,000 times to get the JIT compiler into the equation. And in the assign method, we assign all the 7 fields, like we're shifting the parameter here. And at the end, we put enable to true. And that's it. If I look into the code generated by the JIT, in this case, so I run it. And let's take a look at the generated code for assign method with the help of the commenting on the right, hopefully. You will see that the first field assign, like put field bytecode, is enabled, not my field 1. So it begins by the last instruction of my Java code. What? And then followed by field 7 here, field 6, 5, 4, 3, 2, 1. Completely reversed order. So it really happens. If we change our source code to volatile for enabled, kind of difficult here. So put volatile for enabled. And let's do again a run. Okay. Search for a sign. Good. So let's search on the comments. Okay, first field is, field 1. Why not? Field 7. Okay, some reordering still happen. 5, 6, 5, 4, 3, 2, and 1 are not commented, but they really happen in the assembly. And the last field is enabled. Okay, good. So volatile prevent the reordering of the field enabled. And we have some special instruction also here added. We'll talk about this. So let's go back to this. See?
This guy had a question.
Yeah. Yeah.
What the architecture is testing on and what the JIT compiler is C1.
Okay.
Because, for example, if you are testing on C1 and x86, there is a special case for that part because the M-fence is not the put field behind. It's not enabled with memory fences on 86 architecture. I mean, the 86 architecture in C1 doesn't do this a lot of progress to.
Okay. So the question is on my example, what is the architecture of the processor of my laptop, and what is the JIT compiler, the kind of JIT compiler used? So to answer directly, it's the x86. It's a i7 Intel, and I'm using the C2 compiler. But you should not mix the fact that you have two kinds of barrier, the compiler one and the hardware one. Okay? Yeah. And it's like two different things. Because the JIT compiler can reorder this instruction, and the CPU, when executing the instruction, when executing the assembly code you see, also can reorder instruction inside. That's my next slide. So memory barriers, we have two levels, compilers and hardware. That's very important. So what we saw in my previous example, it's on the compiler barrier. So we prevent reordering of basically the Java instruction to happen. But on the hardware level, there is also the CPU can execute instruction emitted by the JIT compiler out of order too. So depending on CPU architecture, the memory barrier for hardware, there is also memory barrier for hardware, can be required or not. For x86, it's a strong model, so the reordering are pretty limited. But for other architecture like Alpha, hopefully dead, there is much more space to reorder the things, like they can fetch a value before dereferencing a pointer. Let's think about this. It's very mind-blowing, but it happens. On the hardware memory barrier, if we take a look at the schema of an Intel CPU, for example, we have the cores here with the cache levels, the execution unit with registers, and between those two we have some load buffer and store buffer, because the CPU is much faster than even the L1 cache. The latency to accessing the L1 cache is too high comparing to what the CPU is able to execute. So there is some queue, basically, between the two to asynchronously, for example, write the data into the memory. So if we write a field, we will store this value into a store buffer until the L1 cache is able to store it at this speed, this new value. So if we are inside the store buffer, the other cores cannot see my value until it is right back to at least the L1 cache. And then with the cache coherency protocol, the other cores can see this value. So the hardware memory barrier for write, for example, will ensure that when we write this value, we wait, basically, to drain the store buffer up to the L1 cache. And then this value is visible to other cores and other threads. So the hardware memory barrier is about visibility for the other cores to ensure that we see this value at the right time. So volatile in the current implementation of the JVM is implying memory barriers. So for the compiler level, we have preventing reordering of the instruction, and for hardware barrier, we ensure that we drain the memory and there is visibility for the other cores, the value that we just set. So for x86, we have a barrier emitted like this. We saw in my example also. That is the right barrier on the hardware. It's kind of weird because there is some special instruction to emit for barrier explicitly, but in terms of latency, it's not very good. So JVM, JIT compiler engineer, use this kind of hack to ensure the same semantic, but like incrementing 0 on stack pointer. That's pretty much doing nothing, but this is a lock instruction, so we have a memory barrier at the hardware level. For CAS, we have also memory barrier. It's recognized by the JIT compiler and prevent reordering at this level. And for hardware, all lock instruction for Intel means that we have the hardware memory barrier. Okay, good.
Okay. Just to clarify, if people look for the words memory barrier in the Java memory model, you're not going to find it. It's only mentioned about final fields. So memory barriers are from the JMM cookbook, fences are from somewhere else, the atomic classes guarantees are in the Java though, and the Java memory model is yet another animal.
Yeah.
It's a very confused area.
Yeah, so the remark from Nitsan is that the memory barrier is not part of the JMM, the Java memory model. We have no mention of memory barrier. It's kind of implementation details, and there is the atomic classes defined at the Java level, and memory barrier, it's about the implementation details. And it is also, whatever, I lost my thought. Okay. A special method included into the atomic XXX classes is lazy set. Lazy set give you the guarantee also of reordering at the compiler level. There is no reordering of instruction, for writing. It's a write barrier. But the advantage of not emitting the hardware memory barrier that we saw previously. So that's kind of useful almost for performance here, because we don't stall the CPU trying to make the value visible. And most of the time, we don't care about this. So we have still this guarantee that is the most important, that we have not reordering of the instruction, but not immediate effect for the thread. And sometimes, most of the time, it's fine to just, for lock-free, just to continue to spin, to read value, and get when it happens. Okay. Let's go deep into implementation of some lock-free algorithm into the disruptor and the art of the disruptor, and this is the ring buffer. So for those who don't know about the disruptor, who knows about the disruptor? Who knows this library? Okay, a few. Too bad. So this disruptor was released by LMAX as a library. At this time, it was Martin Thompson that was implementing with others from LMAX this library at first. And as he liked to say, this is not new. He's not creating a new things, a new ID. This is just reusing some ID from like the circular buffers in Linux kernel, or the Lamport queue that was older than me. That's like from 1977, I think, if I remember correctly. It's just porting this ID to Java, basically. So why implementing this, knowing that we have, for example, the concurrent link queue that is already lock-free, even wait-free? The guarantees are Well, I mean, the difference between log-free and weight-free and weight-free population behaviors, it's we don't have the same guarantee about the algorithm. Log-free, it's like we have the guarantee that at least one thread can progress in contention. Weight-free, it means that the thread can finish in a finite number of steps. This operation. So the problem with the concurrent link queue, it's like unbounded queue. So maybe a memory issue, and this is non-blocking. It also allocates a node at each insertion. Okay, GC, and not very CPU cache friendly, linked list. And it assumes that this is a multi-producer or multi-consumer case. It assumes that it's the worst case. And we cannot apply some optimization if we have some, like, one producer, one consumer, or multi-producer, one consumer. So it's trying to do the worst case and to be generic. So if we want to use blocking queue, like for thread pool, we need to use the array or link blocking queue that are not log-free. So here comes the disruptor and how it works. Basically, we have a ring buffer target style, array fixed length, with two counters, volatile, by the way, head and tail, initialized to 0 at first, and then we try to insert a new element into this queue at the tail index. We insert the element. And then we increment the tail. And incrementing the tail, we write into a volatile field. So we have some guarantees that we saw previously. On the consumer side, knowing that we have a difference between tail and head, they can try to, there is an element into the queue, so they can try to consume the element into the queue. And that's it. On the code, very simple. We offer insert into the queue. We check if the difference between tail and head equals the length of the ring buffer. It means that the queue is full, in this case. Otherwise, we insert at the tail index modulo the size of the ring buffer our element. And then we increment the tail, volatile right. Very important here because it prevents any reordering. For example, if we reorder those two lines, we insert, we incrementing tail first, and then we insert the element into the queue. In this case, not good because the consumer can say, okay, the tail is incrementing, there is an element into the queue. In fact, not. For the consumer tuple, we check if the tail equals the head, volatile reads here. And if there is a difference, it means that there is an element into the queue. So we're trying to get from the head the index of this element, and we read from the ring buffer. We put null into this index to do not retain the object much longer, and we increment the head. Here we have also a volatile right. Any remarks about the fact that I'm just incrementing a volatile right here? Usually you don't do this very often. I just forget to mention that in this case, I assume that we have only one producer and one consumer for this implementation. That's a requirement for this implementation to work correctly. So as I have those in the assumptions, I can do this safely because there is only one thread executing this. So I can increment a volatile without any atomic things about this. Okay? So this assumption is pretty strong. I mean, usually, in practice, you may have some multiple producer, one consumer. It's more a real case. So in this case, the algorithm is very different. We need to change a little bit our strategy. So if we have two threads, two elements that we want to insert into the queue concurrently, the first thing we need to do is incrementing the tail first. So we're trying to allocate a slot to insert our element. So one thread tries to atomically increment the tail, get this incrementation, and then the second thread do the same concurrently. So they have each thread have their own slot, and at this moment they can insert independently without any issue, basically. So we can insert the two elements in each slot of this ring buffer. On the code, we have changed from previously the basic object array that we have for the ring buffer to an atomic reference array. Not used a lot, but in this case, very important to have this class. It's because if we put just volatile on the declaration of our array, it does not work. I mean, we don't have the guarantee that each cell of this array acts as a volatile field. So we need to use this class to make sure that we have the volatile guarantees for each cell of our array. We change the tail to atomic long, and we just keep the head because we have only one consumer, so no need to have an atomic long for the head. And then we change the offer to this algorithm. So basically, we get the get an increment algorithm, that the loop, the same kind of loop that we have in get an increment, and we check if the queue is full or not inside the loop. Because we may have two concurrent threads that are trying to increment the tail, and maybe we have the edge case that we are full at this moment, so we need to integrate this this check inside the loop. So we get the tail. If with this current tail, we check if we are full or not, and we increment the tail atomically when trying to do this. If this fails, we trying again and reread the new tail value if there is any concurrent thread that incrementing the tail in between. If we have successfully incrementing the tail, we get this to have the index into the ring buffer and set our element into the ring buffer as a volatile write, because this is an atomic reference array. So with this algorithm, the logic is a little bit different. At the moment we put the element into the array, it is available for the consumer. And the consumer rely on the fact that we put the element as a volatile to read this element. So for the consumer, we blindly trying to get from the head the element and to see if it is available or not. So if the element that we get at this moment is null, it means that the queue is empty. With the slight remark from Nitzan that for if you want to implement this algorithm to stick to the contract of a blocking queue, just a queue contract, there is a subtle bug, a race condition, that in fact that we may have the queue not empty, but not the element inserted into the queue.
So it works except for the little bug.
it works, but there is a slight. I mean, it's if we stick to the contract exactly. So what the user can expect from the behavior of this method. That's correct.
Yeah, it's just that it may not be empty. You can't get the next element, but that doesn't mean the queue is empty. If you go back to the previous slide, you can show why.
Yep. Super. No, this one.
So you can see that we can increment the tail. So one thread increments the tail and stops. It's interrupted. It's now suspended forever. Right? And then the other thread increments the tail as well and then writes. So now we have an element in the queue and the slope before it is still null. The cursor can travel without the elements actually getting into the queue. Now, is it a real problem for real use cases? Probably not, but it can happen. It can, if your library relies on when I call something and I get null, that means the queue is truly empty, and that's not the case in this case. Is it a good implementation to have a poor method that does this? Yes, because it's less contention. But you probably shouldn't call it poor. You should call it weak poor or something like that, because other people have expectations from the queue contract. And they get confused. They call you up. They blame you. All sorts of things happen.
Okay, thank you for the compliment.
People nag at you while you present.
Okay, thank you, Nathan, for the remark. Yes, question.
I got a question. What happens when you run out of integer space? Do you keep incrementing numbers?
I'm using long.
Okay, right, good.
Yes, and in the first implementation, I was using the integer, but yes, in this case we are using long, so we are pretty much fine with this. So the question was about if we are running out of integer, but we are using long for this implementation. Okay, so disruptor, that's it, basically. The basic heart of disruptor is this. There is plenty of classes, strategies around this to have different usage. And there is also, because what you see is a naive implementation, there is a lot of optimization on top of it. You can see those optimization into the GIC tools repository made by Nitsan. There is also a good article about this in his blog. And the problem with the disruptor for our case is we may be if we are instantiating a lot of disruptors, the requirement is that we need a consumer thread each time for this. And for our case, if we are a lot of disruptor, it means that we have a lot of threads into our application and put a lot of pressure into the kernels because they need to arbitrate this. So we found out that there is an interesting algorithm. There is an article of Intel trying to make an example of how to parallelize different tasks and still get the result in order. So, for example, if we have a video stream processing and we read frame from an input, it's obvious that we can parallelize the processing of each frame, and encoding or whatever, and we need to write into the output stream in order. Otherwise, this video would be a little bit scrambled. So basically, we read from this input in order, we parallelize the processing of each frame, and we want to write into the output stream, but in order too. So how to keep this order? We use the order buffer technique. So the disruptor can do this, but with a consumer thread, as I said. So we want to get rid of this consumer thread, and we use the thread that are into the task, that parallelizable task, to do this ordering. So the order scheduler is implementation of this ID. So we don't have any inter-thread communication with this. No additional thread for consumer. We just have the thread that processing the frame, and we don't have to do a wait strategy on top of it. We just need to take a ticket for each frame. So the idea is we have 3 threads here with each one have a ticket. We have still a ring buffer target style structure with only one tail and initialized to 1 for the first ticket. So the first thread with the ticket 1 comes into this structure. The tail and the ticket matches. So we process this. And then there is another thread, but this ticket 3 and not ticket 2 that coming into our structure. Here the tail and the ticket doesn't match. In this case, we insert our element into the index of the ticket to make the processing after. So we give up, the thread give up the element of the processing and continue and proceed. And then we have the second thread of ticket 2 that match the tail. And in this case, we process the ticket number 2 and we reuse the thread, we increment the tail, and we reuse the thread to process the remaining element into the buffer. And we proceed. We increment the tail. There is no element into the queue. We can end the processing. Very simple. So we previously have this kind of code with a big synchronize here. So we read the process, we have an input, we process this input, and we write in order this output. So if you basically doing this, if you want to keep the order, you need to have a big synchronize, big lock on this. With the order scheduler, we can keep this for reading and get a ticket from the scheduler associated with this input. And then we process the input concurrently. And then we make sure that with the scheduler and the ticket grabbed before with the input, we write into the output in order of the ticket. Don't forget to trash the ticket if you have any exception during the processing. Otherwise, you are blocked. So we open source this implementation on GitHub. On my last slide, I have 3 slides of references with the links. It's open to pull requests and can discuss about this, about the design of this implementation. And we use it internally to do some reducing of the contention, but not adding each time a consumer thread. So for this presentation, to wrap up, we have learned how to measure our contention, how to atomically update a value. That's a basic primitive for any log-free algorithm. We have learned about the memory barriers, how the disruptor work with the ring buffer structure, and how to order some parallelized tasks. I will not go deeper, but there is on my slide, I will tweet about the link about the slide with all the references grabbed for this presentation. So we have 3 slides of references, so we have plenty of reading for you, including the JSC tools, blog from Nitsan, because it's a lot of information in it. You can learn about this a lot. So if you have any questions. can do this. Maybe if you have used this. Hi. Hi. Any question? No?
Going once.
You're good for my talk? Maybe they are sleeping. You need to.
Fantastic.
Here we go.
Cool.
Thank you.
Thank you very much.
Hey there. We have Mr. Kukshenko, please.
Right. Can we steal your...
Hey, yours, yes.
Thank you. Does that,
Does that what? It would just work.
It'll just work. Yeah. It's okay. Whispering when you're mic'd up is really fun. Because it sounds to you like you're talking really quietly, but you're not. Okay. You need to switch it on.
It's not.
Damn it.
There you go.
All right.
Wow, wow. That's got to be the smoothest transition between speakers in the history of talks, right? It's fantastic, fantastic. So my name's Richard.
I'm Nitzan.
And yeah, fantastic.
Yeah,
We're going to be talking about JVM profiling under the hood. And that's a talk that's fantastic. I've got a pointer as well. It's this under the hood. It's a talk that's so gangster I had to wear a waistcoat in order to present it.
There's an earlier version where he just wears just a vest, no shirt, nothing.
That's what we call deep dive.
Yes.
Yes. Okay, cool. So, what are we going to be talking about? Firstly, we're going to talk about why you might want to profile your code, why you want to get those insights to begin with.
Why indeed?
Why indeed?
Tell me.
Then we've got a section called lies, damn lies, and statistical profiling, where we're going to be looking at some of the problems, biases, and things that you might encounter when using your profilers, where they might not be entirely honest to you, where they're telling you that the wrong part of your code is taking up time. And then we're going to look at some possible solutions, and we're going to talk through a few different profilers and techniques which solve these kind of problems, which can use to get a more honest view of what's going on in your application.
And eventually we will have a conclusion for you. So
yes.
hang in there.
I should probably caveat that at some point in the middle of this talk, there will also be a coffee break. So if you're sitting there in your seat with your hands shaking, going, how, I've not had my morning coffee yet, it's okay. Come 10:30, or no, not 10:30, 11:30, we'll be breaking for a bit in order that you can drink some. So that's good. That's good. We are enabling a coffee addiction. Cool. So why would you profile? Well, sometimes you get situations like this. Not necessarily a bus going through the middle of a motorway, though one does begin to wonder how you got to that point in view in the position. But you get a kind of situation where your application is doing some task and you get some kind of performance bottleneck. You kind of get some performance problem. And there are two approaches to solving this kind of problem, right?
Probably three.
Yeah. Probably three. Well, approach one is you take this dog as your role model and guess what the solution is. Now, when I say guesswork, that might also include things like, we had this problem before, therefore we need to apply the same solution. It might sound a bit like, oh, it's probably that Java EE library. Everyone says that's slow. We need to rewrite it in Node.
You can also try to stop and start your application. That
Yes.
seems to work for most things in life.
Yeah, that's also basically guesswork. There are lots of things. But we're here for a kind of a more informed perspective on that kind of thing. We want to talk about solving problems by measuring data from your application. Jean-Philippe talked about using lock profilers earlier to identify contention points, and then we could refactor. And Sergey is going to talk after our session about using instrumenting profilers and some of the solutions that you have in that space. So really, the kind of running theme from this session is you want to be measuring data from your application.
So one other reason for profiling, people don't talk about it as much, but is just to explore your application. I think a lot of people don't do it, but let's see. Who's never used a profiler in this room? If you've never used a profiler. Who uses JVisual VM? Awesome. Who uses Java Mission Control? Okay. Who uses some exotic profiler? That wasn't much. And therefore, yeah, some of you were lying. It's just, I'm just saying, putting it out there. We
Or shy.
We should try and be honest with each other. So you can crack up a profiler, look at your application, and it'll tell you a lot about the code that's actually running, as opposed to, you know, looking at the code base and saying, well, there's only 3 classes here, it must be one of them, right? Maybe when you actually run your application, you're using a gazillion frameworks, and that's where everything comes together, where the time is spent. So opening up your profiler is a great way to actually get to know your application as it runs. So have fun with that.
Exploratory profiling. Fantastic. Quick hands up. Who's done some kind of exploratory profiling? Just some profiling to see what's going on with their application when it's quiet. A few people. Cool.
Kirk is one of those try profilers. He would try anything, right?
Cool. So when we're talking about profiling, what are we talking about? Well, there's lots of different ways you can profile your code. You can do memory profiling. You can do cache profiling. But what we're actually going to be talking about for the bulk of this talk is execution profiling. And execution profiling is profiling that's trying to answer the question, where in my code base is my application spending time? It won't tell you why you're there. It won't tell you what person wrote the code in the first place. It won't answer any of these questions. It'll just tell you where in your code base is your application spending time. And in fact, problems like execution profiling are useful, but I don't want to present this as being something of a complete panacea. There are all sorts of different other problems that your application might encounter. Execution profiling is probably not the best way to investigate, for example, a garbage collection problem. It's not going to help you tune your networking setup or anything like that. It's not going to help you, say, figure out which of your database indexes you need to fix or any of those kind of problems. And there are also a lot of things which are still CPU bound, but might have kind of queuing effects or timing effects in them, and execution profiles are probably not the direct best route for investigating those kind of problems. But if you've got a CPU bound bottleneck, or you just want to see what your application is doing when you hit a problem, execution profilers are an invaluable tool.
Indeed.
So,
but they're not all the same.
They are not all the same.
Shock. Horror.
In fact, sometimes you get this effect. Did anyone go to like Hall of Mirrors when they were a kid?
You see, not all of us had the same childhood as you rich folk.
Nobody went to fun fairs when they were a child?
Who had an ice cream as a child? Nobody. Who lived in a shoebox in the road?
Okay. I will find like a melted ice cream as a distortion effect in future. So, but you get these funny mirrors, right? And they sometimes make your belly look bigger or longer, or you've got the diet mirror that makes you look nice and thin, that kind of thing. Profilers can sometimes have the same distorting effect. They can take a certain part of your application and make it look as though it's eating up a load of time, and they can take other things and make them look like they're using up much less time than they really are. Cool. And there are different forms of execution profile as well that we can think of. We can talk about instrumenting profilers versus sampling profilers. So these are two key different approaches. And an instrumenting profiler basically goes there, takes all your code base, and adds in timing instruments. So you've got like a method call, and it'll get the time at the beginning, it'll get the time at the end, it'll subtract the two, and it'll try and store that in some data structure. And there are some problems with instrumenting profilers, right, Nitzan?
Yeah, so well, I like to think of it as a metaphor. It's like two kinds of manager you may have. One manager will ask you to fill in a timesheet for everything you do. You took a pencil, you put it back, you looked at the wall for a bit, you touched the keyboard, then you thought about it again. You'll fill in a form for everything you do, right? And then there's the other kind of manager who just walks by a cubicle and says, hi, every once in a while, what are you doing? You can have the intrusive manager who just shows up at your desk all the time, of course, which is why sampling profilers can affect the behavior of your application as well. But an instrumenting type of profiler will change your code to investigate your code. In my experience, far more than a sampling profiler would impact your application. So instrumenting profilers are good for some things, but they tend to come at a cost. And in any case, we're not going to talk about it too much. So
yeah,
let's forget about them.
So the main focus of this talk is on sampling profilers. And what sampling profilers do is periodically they take a snapshot view of what all of your threads are doing, like, kind of like a stack trace view, and then they aggregate these series of stack traces and present you with a view of either what method they see most often, or maybe a kind of tree view where you see what's calling that method when it gets executed frequently. So something like this happens. You've got a method in your application server, your web server that's sitting there running at the bottom. You've got some controller code that's doing something. You've got you're reading a database object out. You're building up your person, and then once you've got this database value, you send off to some view and generate some HTML, and then your server's going to do something else. Okay? Obviously, real frameworks like Spring have like 300 entries in their stack trace. Not 300, but it's pretty close. It's getting closer, right?
Which is great.
Which is great. It's great. But what your sampling profiler does is it comes along and says, here's a snapshot view. So the first profile will say, right, I'm in the web server's main run thread. The next one will say, I'm the constructor for the person, inside the read person, inside the do something, boff, 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 boff. And having sampled repeatedly, you can get an accurate view, or possibly accurate view, as we'll see, of what your application is doing over time. Yes.
So it's the more samples you have, the more statistically accurate your profile is going to be. That's the general idea with sampling. But
there are a number of problems. So the first bias that you might see, which we mentioned first, because it's actually probably the least problematic of all the things we're going to talk about, is the concept of periodicity bias.
Shit. We'll be right back.
Fantastic, fantastic. The periodicity bias concept is you're profiling at a fixed interval. So you have a bias towards what your application is doing at that fixed interval. If you have periodic applications in operations in your application, maybe things take a certain amount of time, or maybe you have timing-based operations with the same frequency as the samples, but skewed off or on, that can have a bias in your application. So, So here's an example where you're intermittently calling two methods, some method called A and some other method, and you never even see what that other method is because your period always aligns with you running A. Now, periodicity bias is incredibly unlikely to happen in your production application, but it is possible. It is possible. So let's look at something that's a little bit more problematic, shall we?
Give it to
you.
Give it to her now.
I'm handing the baton over. Okay.
Okay. Right. Okay, so we're going to look at stack trace sampling, which is what the sampling profilers do, most of the profilers people use the JVM-TI interface. They call something get call trace, and that method triggers a global save point. We'll get to what a save point is in a second. It doesn't trigger a global save point on Zig, but that doesn't actually matter much. It causes slightly less damage when you do that on Zig, but who cares, right? And it collects a stack trace. The impact on the application is large. It's sort of like a stop the world mini pause. It's not a huge pause, but it will take all the threads, sometimes one at a time, sometimes all together, and walk through them, collect their stack traces. And it only samples at those save points. And the example we have here is, it's your example. You can, I'll click.
Okay, fantastic.
I'll click.
So I've put a few samples up on my GitHub. There's one class here called SafePoint bias, I think is what it's called. And you can just use these, you can just run these in their main method, no dependencies or anything, and just try other profiles against them. So if someone's trying to sell you anything or what have you, you can test it, you can measure it and see what's going on. This is a very, very, very simple piece of code, and it's mainly here as a demonstration of how this bias can impact you. So we have a method called outer, and outer just has a loop where it's counting up this I from 0 to outer and passing that into hot method, our hot method. So our hot method code takes an array, loops over the array, a number of times, takes an index, and adds in all the elements after that index to that value. So it just does some very, very basic, very, very simple arithmetic operations with arrays. Importantly, these are both integer index loops, and they're both counted loops, as we'll see in a sec. Now, what happens when you run this code and you attach JVisualVM to it as a profiler is you get a result like this. You see the main method, which was at the top level. You see that outer method, but that hot method isn't even visible to you. It's allocated 100% of the CPU's time to the outer method without saying any time was spent in the hot method. Quite wrong.
But why?
But why? But why? Not only that, we can run the print safe point statistics option on our JVM, which will it'll give you a whole bunch of different text output. But I'd just like to draw the attention to a couple of things. Firstly, I'm going to talk about what a safe point is, but we can see that we've had a series of safe points caused by thread dumps here. And the other point is, as we say, this is a stop the world pause. And to get to that pause, we've got a maximum sync time of 985 milliseconds. Now, that profiler was trying to profile once every 10 milliseconds. So trying to get there once every 10 milliseconds, trying to get a sample. And in some cases, it took nearly a second in order to actually be able to achieve that sample. So why is it sitting there confused, and what can we do about it?
All right, so let's just think about what's a save point. Save points are not a necessary detail of JVMs. They're not like inherent, but all JVMs have them. It's the common practice to implement JVMs using save points. I think there were at least a couple of commercial JVMs that didn't use save points, but they're no longer with us. OpenJDK has just a single global save point flag, and it appears in your code you will have save point pulls. Every once in a while check, do I need to stop and let the JVM do its thing? And where you'll find those save point pulls is at the back edge of uncounted loops, and you'll notice the little quote around that, and at method exit or method enter, depending on the JVM. The reason I put the counted and uncounted in quotes is because it's, some would say heuristic, some would say an arbitrary decision, but it's the JVM compiler writers, in their wisdom, decided that int loops and smaller integer types are going to be short loops. So I'm not going to worry and stick a save point in there. I'm just going to blast through them. Long loops, however, are long. So I don't know how long that's going to take. I'm going to have a save point in there. And while loops, or loops that I can't prove the sort of stopping criteria, and it's not a simple for loop, I'm just going to have a save point on every iteration. So it's one of those heuristics that mostly work, but it's a bit of an arbitrary decision where those save points fall. And a save point pool can be delayed, as Richard has experienced here, by long-running counted loops, but also just by very large methods. You have a very large method that has a lot happening in it. Methods can get very large. I can't remember the exact limit on method size, but I think it's in the kilobytes, right?
Large methods, like it's like for what the hotspot definition of large methods, like 8,000.
Yeah.
So bytes in size.
As a bonus, anything can get in the way of your thread executing. So I can suspend your thread or interrupt your thread. Not the Java sort of park method, but if the OS interrupts your thread, so you have a gazillion threads, they're all trying to run, they will bump each other off. Maybe one of them is low priority and the OS takes these things seriously and it'll be stuck in the run queue. All of that will serve to stop your thread from reaching a save point. So I have this lovely, colorful slide here.
So just to caveat, this color here is red, this color here is yellow, and this color here is green. Okay?
Anybody colorblind in the audience?
I'm sorry.
I'm sorry. No sense to you at all.
Don't worry.
Right?
Even if you weren't, the colors would still be indistinguishable.
Okay. So we have two threads. Lasers. We have two threads here. We have two threads here. We have this last thread here. Why are they different colors to those of us who can tell the colors apart? Right. The red thread is blocked. Blocked threads are at a save point. In fact, if your thread goes into native code, it's at a save point as well. It doesn't mean it's not running, but it's effectively at a point where the JVM doesn't care what it does. Okay? The yellow threads are those miserable on the run queue threads. They're just hanging around waiting to get on a CPU. And we have two green threads here, and those are actually on call. So somebody wants us to stop. They called raise the global save point flag. And Mr. Green here, he's a polite citizen. He stopped pretty much straight away. He reached the save point pool. He found out everybody has to stop, and he stopped. Those apparently yellow threads, they now use the free core, and they get in there, and they get to the save point, and they stop. This one, however, has just kept going this whole time. And there's a measurement that is not included in your GC logs, but you can make it show up with this lovely little flag here, that reports the time to save point. The time to save point is from when I asked the JVM to stop at this blue line and until I got to this red line. And in the middle, hammer time, the JVM gets to do its thing. So it wanted to get to a save point because we asked for a thread dump. And then we spent all this time waiting for it, potentially more than we actually end up spending it at the save point. We could wait for the save point to happen longer than we will spend at the save point. Okay? We exit the save point, and then life goes on, and everybody gets in each other's way again. So
we should caveat that it's worse than this scenario as well, because the get call trace method doesn't call one global save point, stopping all the threads and collecting the information once. It calls it once per thread. So if you have like a thread pool, like a servlet container with 100 threads, for your profiler to sit there and collect information about what it's doing, it needs to go through this process 100 times in order to collect the data.
All right. Shock, horror, unpleasantness. All of these things happen, and more, right? So we said, where does the save point pool happen? And the fact that these profilers only sample at a save point. The C2 compiler, C1 compilers, inlining methods is a great thing. It's a very good optimization. It expands the horizon of possible optimizations. It is the mother of all optimizations in many an opinion person's mind. But because of inlining, when we inline a method, we effectively remove a save point pool. So we lower the visibility of that method when you profile with save point bias type of profiler. And what we see here is that what we thought we were profiling was this sort of sample every period of time. But because all of these methods got inlined, I can't see them with my profiler. I can only see the save point at the end of do something. Okay, so all of these samples that I thought I was taking in the middle, they all ended up waiting for the end of this method. All of these intermediate events just disappeared. And this can happen, it does happen. Is it the biggest tragedy that ever happened? Probably not, but it does produce a bias in your profile, and you may end up profiling the wrong thing. But there are some profilers that will work correctly. So this is Java Mission Control. And as we can see, can you guys read the text on that slide at the back? No. So I'm going to read it out for you. It's OK. It's calling the main method in this class. It's calling that outer method in the class. And it's calling the hot method inside the outer method. And it's attributing 95.32% of application runtime to that hot method. So it's got the method. It's got the information. It's giving us an accurate view of the world. Yeah,
fantastic.
If you haven't tried Java Mission Control, it is free to use on a developer machine. It's a lovely profile, both visually and in terms of the in-depth information it gives you. And give it a go. I think the next time you have to pick a profiler, it's a great profiler to use. But we're going to have just a counterexample to show that not all is one-sided. Your JVisual VM type profiler will not let sleeping dogs lie. It will wake up every thread that is sleeping and ask it, what's your stack trace? Okay, it won't actually wake it up. It will get its stack trace. The JMC type profile, or the CPU sampling profilers that interrupt running threads, they only interact with running threads. So if we have an application that is mostly sleeping, which I hacked out of some code I had lying around, we will see that over a minute, all of the time is spent in thread sleep. And you will notice the two columns at the end over here. We have total time, which is actual wall clock time sampled. All of these samples I spent in thread sleep. But there is no CPU time spent. That thread didn't spend any CPU cycles. This is awesome. This is exactly what I wanted to know. However, when I look at it at Java Mission Control, thread sleep doesn't show up at all. And you'll also notice that the sample count is very, very low. The reason the sample count is very low is because the thread is never on CPU. It's not getting interrupted and sampled as it would do with the profiles we're going to get into in a second. I think that's we're just on time for break. Yeah.
So we're just going to take a coffee break. There's coffee outside. And we'll be kicking off back here at 12 o'clock?
Yeah.
Something?
Something like that.
We'll be back here at 12 o'clock. You will hear our booming voices outside once you've had the coffee. So that'll be fantastic.
Awesome.
And we'll be talking about how you can solve these problems and profilers that solve these problems and how they work. Thanks. So, people enjoy the coffee?
Yep.
Fantastic, fantastic. 3 people enjoyed the coffee. Okay, cool.
It's terrible.
Terrible. It is, yeah. Okay, but now we're going to talk. We said we've got a lot of problems. We've said no profiler is absent of biases, but some have more than others, and they have different biases. But let's look under the hood for things which at least solve the safe point sampling bias, and let's have a look at some of the interesting characteristics or common implementation characteristics that they all share. In fact, we're specifically going to be looking at one profiler, which is an open source profiler.
And who could that be?
And
Who is that person?
That's me. But there are other people have contributed to this code. You've contributed to this code.
It's partly
some
my
people from
fault.
Google dumped some code. We'll look at that in a sec. But we're going to be talking in detail at this one profiler. But importantly, a lot of the implementation characteristics which make this work are not related to this blob of open source code. They are things that are in the OpenJDK, things which are in your operating system, and they're common implementation techniques, which a number of different profilers share, and we're going to be talking about those different profilers as well. So we will give a more well-rounded view as well. But this is something which is good to deep dive on, because you can see how it works or doesn't work or whatever. Fantastic.
Just about works.
Just about works. And importantly, the important characteristic of Honest Profiler is even though it has a very ugly UI, in our SafePoint bias example, it does find the hot method as being the method that eats most self-time, most CPU self-time. So it does pass our test for something that doesn't have the SafePoint sampling bias. So how does that happen? Well, under the hood, it's using, you remember earlier we said there was that method in the JVM TI API called getCallTrace. Well, there's also this other method called async getCallTrace. Quick hands up. Who had heard of getCallTrace? Who's heard of async getCallTrace? Fantastic. This is good education. So async getCallTrace is a non-standardized API that was introduced into the JVM so that what is now called the Oracle Solaris Studio performance analyzer can profile code.
Does anyone use Solaris Studio, by the way? No.
Sergey, you should hopefully be putting your hand up at this point.
Solaris Studio? Just put it up, whatever. Yeah.
Importantly,
yes.
It doesn't just work in Solaris. It's a terribly named product. Yeah, it works on Linux. It works on a lot of other things. And also, unlike many other products by Oracle, you can freely use it. So that's quite good. The implementation there is actually adapted to an open source prototype by a guy from Google called Jeremy Manson, who works on their JVM team internally. And it's quite a cool prototype. It showed how you could use this API from another tool, but it had a number of limitations. Like you couldn't switch the profiler on and off, and you couldn't actually view the results whilst the application was running, things like this. So it was very prototypey, but that's where the original code came from that developed into Honest Profiler. But this async getCallTrace is the approach that's used by Oracle Solaris Studio, and a couple of other profilers, as we'll say, they don't necessarily use the same method call, but they use fundamentally the same techniques. So, what is actually going on? So we said we're using this method call. Why does it actually work? Why is it different from our getCallTrace method, which, remember, had to stop all the threads n number of times with these massive safe points? Well, under the hood, this uses something called sigprof. So everyone done some kind of like kill-9 or something like that? Yep. So you sent a signal to a process on Unix, and those signals all have numbers. And 9 is like just kill the darn thing. Well, sigprof is the profile signal that's associated with profiling. So you can configure your OS to repeatedly send a sigprof to a running process, and it will interrupt the thread. So it's an OS-managed timed interrupt. And it will interrupt the thread no matter what it's doing, as long as it's running, not sleeping, which is why, as we saw earlier, Mission Control, which uses a similar approach, didn't give you any information on sleeping threads. But if the thread is running, that's what we'll call. And what it actually does is it calls some event handler. This event handler is not written in Java. It's a signal handler callback, which needs to be written in some kind of native code. And all the profiles we're going to be talking about for the next 10, 20 minutes something are all using this same OS-managed timing interrupt.
Yeah, just a quick point on running threads. If you use JStack and you get all the states of all the threads, some of them say running while they're actually parked, for instance. When we say running, in this context, they are on CPU. They are actually the scheduled threads. So it's not the threads at the back of the run queue or the threads that are sleeping. These are the threads that are actually running on core.
Yeah, fantastic. So SIGPROF, pretty cool. Here is a lovely diagram. We had to have some kind of architecture diagram in the slides. Beautiful. Look at this aesthetic. Lovely, lovely. No expense spared. So what's happened is we've got our OS managed timers, and the application has some series of threads which are running. And the OS managed timer will interrupt those threads and will have registered a signal handler. So a signal handler is like, here's a C function that gets called on that thread when the interrupt happens. And signal handlers are quite special in some regards. And I mean special in both the nice way and the nasty way as well. They are quite restricted in what you can do. Because you might be calling any existing function, for those functions to be callable within a signal handler, they need to be what's known as reentrant safe. That means you can call them whilst you're in the middle of calling them somewhere else in your stack trace, right? Because you could interrupt the calling when they're calling. It's basically the Yo-Dog meme all over the place. And what that means is you can't allocate memory, you can't obtain a lock, you can't even use things like memsets. There's lots of things you can't do. It's very restrictive. So what you want to do is, as quickly as possible, and again, I think this is a basic architectural approach that pretty much all profilers using this kind of technique use, is you take the data as quickly as possible and write it into a lock-free, allocation-free ring buffer. So, you know, a circular array, and there's a bunch of slots, and you just keep on trying to write values into that ring buffer. And then you have another thread here, which is not sitting in a signal handler, and it can do useful things like look up the actual name of the method that's being called, because obviously that's a piece of information you want, right? You want the method's name. And it can also do stuff like write it out to a log file or whatever. Honest Profiler has both graphical and console UIs for reading that log file and can read them online, just that's to say, whilst the profiling has actually happened. Okay? Fantastic. So that's the overall approach. And you're a maze of twisty little stack frames all alike. So it's time to pass the baton back to Nitzan.
Thank you. So we're going to have to look at how async get call trace is implemented on the JVM side. We won't get into all the details. Gladly, OpenJDK is open source, so you can dig in and lose yourself in beautiful code.
Spelunking, 20% time.
Yeah. So Richard mentioned there's a lot of things you can't call in signal handlers. You can call async get call trace. I think you can't call get call trace because of all of these restrictions.
It'll allocate memory.
There's a lot of bits of the JVM that you're not allowed to call. This is the one method that is exactly for that. So, right. We're going to have a look at async and call trace, how it's implemented. So let's start with what happens when a signal handler code is fired. You're sort of like Agent Smith in the Matrix. You possess a thread. It's the same thread. It was doing something, and you just land there. And to get the call trace, you're going to have to figure out where you are. And the information you have is those acronyms, the PC, the FP, and the SP. So there's 3 registers that we use to deduct where we are. There's the program counter that tells us which, where's the instruction pointer pointing at. There's the frame pointer, and there's the stack pointer. And we're going to use those to figure out the call trace. And the API we have is that we need to return a call trace that has a Java method ID, so we need to look those up. And we need to find the BCI, the bytecode index, which would later the profilers would use to find the line number. Confusingly, it's called line number in the data structure, but it isn't. Okay. So given a program counter, given the sort of instruction pointer, you need to find which method you're at. And you need to find if it's a Java method. The JVM has handy data structures for doing that. You look up the Java method for that particular program counter, for that particular instruction address. And if you find it, great. But if not, what are you going to do? You're going to have to sort of climb out all the way up the stack and find out if there is some sort of Java method above you. And then let's say it is a Java method. I have the instruction counter. How do I know which line I'm actually at? So the problem is that not every instruction maps to a code line. We have an example that we just talked about. Save point polls are assembly instructions. There is no Java line of code that corresponds to them. There's a lot of similar cases where the compiler comes along, scrambles all your code, and now it's very hard to say which line correlates to which instruction. And there's a very simple solution to that. We just find the closest one. So there's a bit of inaccuracy happening right there, right? Also, what is that sort of instruction counter? Because who knows what a superscalar CPU means? You know what that means? Right. CPUs, modern CPUs, can do more than one thing in one cycle. So you get one cycle, and the CPU will do like 4 instructions in one cycle, 5 instructions in one cycle. So if that's the case, where is the instruction pointer? Is it any one of those particular instructions? Because it's just pointing to one. And on top of that, what's the limits of program counter accuracy? And this is a chat between Brendan Gregg, who is this big profiling guy, and you should look him up and read his blog. And
he's not physically large. He's just famous. He's just famous.
His presence in that space is huge. And he says, and he mentioned it to me that they're no longer reliable. And then he said, they never were, right? So the problem is you ask the CPU to stop, and then it skids. It's like, you're running, and I say, stop. And where we stop is slightly after where you actually were, and that generates a slight distortion on that part. So again, even at this level, there is a limit to the accuracy we can offer with profilers. So we have this limits to the line number data accuracy. So we're going to have skid, and we're going to have the line number lookup issue, which we're trying to find the closest instruction, the closest line to the particular instruction. There is a JVM option we can throw in to increase the data on that side, which is quoted there. So if this is an issue for you, you can try and give that a go. There's not much you can do about the skid, but it's worth realizing if you ever end up looking at the assembly profile. And now we go back to the stack. We have who knows what the stack looks like roughly on an OS? Okay. The stack is sort of like a linked list, single linked list. You're at a particular frame, and you can, in theory, walk up all the way to where you started. So when you pop your frame, you're back in the frame you were. And the frame is, the sender links back to whoever called me. I point to the stack so I can find all my variables and arguments. And I have the program counter, which is where I'm actually at. Okay, and this linked list is going to be converted into JMethod ID and line number. So this is what a typical stack would look like on a Java program. We would have the sort of infrastructure of the JVM launching a thread, and then we will have interleaved Java frames, and we will have some native frames as well. So we'll have interpreted code, we'll have compiled code, we'll have native code somewhere in between there. And the top frame may be Java, may be native. All of these frames we're going to have to climb through, even though the native threads we're going to ignore. We want to know what happened before them. We want to have a full picture of the call stack. So if you call into JNI, sorry.
I was going to say, it's worth noting the fact that native frames are ignored is also a bit of a limitation of something like the async get call trace based profile. I mean, it's also a limitation of JVisual VM, but the fact that once you have, say, a bunch of code that eventually calls JNI at some level, you don't really have very good visibility into what that native code is doing at the bottom of your stack trace. Yeah.
Yeah, so it's... The sad thing, in a way, is that we are going through that. We could have provided that data for roughly the same price. That's not what the API offers. It only gives you the Java frames in the deal. So some native code would use the frame pointer as a means to reconstruct the stack from the data we have. Some of it won't. Some of it it's compiled out or in. So we don't rely on it in OpenJDK. We use the last remembered Java frame instead. And then we find Java frames. Java frames are a different kettle of fish altogether. They don't have the frame pointer because the JVM throws it out. So a lot of tools don't work with Java code because of that, because the frame pointer isn't there. There's an up-and-coming change to the JVM to include frame pointers, which would enable another class of profilers to interact with the JVM. And there's certain challenges in looking at Java code from an interrupt handler. So if you dig into the code, you'll find there's a lot of specialized code that's only getting used from async get call trace. And it's designed to give up in certain cases where the code is actually moved while you're interrupting the thread, or if a method gets recompiled. So if you interrupt the thread while it's de-optimizing a method, the async get call trace is basically going to say, I'm giving up. I don't know what's happening, and you can sample again later. So that's Java compile threads. We have interpreted threads, interpreted frames, which in theory should be simpler, but they're sort of a special case, and they get managed both on the stack and both in their own data structures, and then you can interrupt the interpreter halfway through allocating a frame, and then you don't know where you are. So great fun on the async get call trace trail. And then you have virtual frames, because the fun isn't done, which is what happens when you inline. You want to know about the inlined methods, right? You want to see that line of code from whatever that new person constructor was that was buried 10 levels deep. So the JVM is going to have to look up some debug info for you to find that piece of information out, and it'll have all the data about the inlining. There's no data on the stack. Which leads me to the limitations here. It only profiles running threads, as we saw before, right? The accuracy is limited by reality, and reality is sad, as we all know. And it only reports the Java frames and threads. The last one is an interesting one. It has to look up debug info during the call. That's a limitation of the API as it's designed, because it has to return the Java method ID. It has to return the line number. If it was a slightly more bare bones sort of API, you could have built other profilers using that information. You could have done those lookups offline, which is what Perf does, and it's what ZVision does for Zing. So you take the stack trace, it costs you a little less, and then you do the offline processing separately.
Cool.
Off to you.
Thank you very much. And if Nitzan sounded there like he really, really hated async get call trace, it's because he's been recently implementing async get call trace for the Zing JVM. So there's justifiable reason behind his hate. There's also justifiable reason behind my hate, because compilers, for me, are simultaneously a great friend. They give you nice, free optimizations. That's fantastic, efficient code. But they're also a terrible fiend. And we're just going to talk through a couple of the other issues which we kind of encountered when writing Honest Profiler, which are kind of interesting anecdotes, things you might find interesting for understanding what it is to be working with these kind of signal handlers. So, as we said, there's a restriction on the methods that we can write in order that we can call inside our signal handler. So we can't call memset. So we just want to blast out a bunch of memory and say it's all zeros. And we can't, and memset's the C function that we use. To do that, we can't call that. So nice, simple, safe reset function. You may not be a C programmer, but this is obviously, or C++ programmer, but this is obviously, just taking the beginning of the array, looping over it, and blatting out some memory on its way through. Nice and simple, nice and simple. So if we take this code and we give it to GCC at optimization level 3, what do we think happens? So put your hands up if we think everything is correctly compiled and works fine. Put your hands up if you think it's a complete disaster and makes Richard really angry. Fantastic, that's the correct answer. So what happens is it produces this code. So this is on a Unix OS. So just a caveat, what are we doing? RDI and RSI are the first and second parameters. So that's like the beginning of the array and its length. So we add them to find the end, and then we compare the end and the beginning. So that's like saying, if the array's size is 0, just jump to L3, which is return. So if the array is empty, just don't do anything, just return.
And
that's fine.
Focus on the positive here. This is a nice optimization the compiler did for you.
That's lovely,
that's
that's lovely.
Grateful.
And then these three assembly operations happen. So that says get the length back by subtracting RDI from RDX, and then blat out this ESI register, because it's going to be used by the function we call, and then call the memset function. That's right. We wrote this code to avoid having to call memset, and GCC came along and said, you, the user, are really stupid. You don't know what you're doing. You've written memset. You should just be calling the memset function that's built in. So I'm going to optimize your code to just call memset. And it will also do these things with things like memcopy as well, which has a similar problem. This was worked around by just disabling the optimization. So there you go. Compilers can be really patronizing.
Yeah. Who thinks the JVM does this to your code? Anybody thinks the JVM is cheeky and would dare do something like that to your code? Right.
Fantastic.
Sometimes.
Cool. Also, concurrency bugs are fantastic. I love concurrency bugs. So there was, interestingly, an unspotted race condition in the ring buffer, which was entirely my fault for being a complete moron. Boo, boo. But this is actually a really interesting one to mention, because I would never have spotted this, even though it's quite a simple bug, because everything looked like it was working fine to me. Or I tested the code, it looked like it was working well. And it was actually spotted due to this guy called Rajiv, who put a GitHub pull request, a really awesome GitHub pull request, this hugely detailed description of this bug in this ring buffer. So this is also a great example of someone doing open source code review and spotting and fixing bugs. Nitzan also did a couple of great ones for some weird scenarios which were segfaulting the JVM as well. So open source, fantastic. So what was this concurrency bug? Well, remember I said we had this lock-free, allocation-free ring buffer. So we've got this series of slots, which conceptually are like a circle. The green document is the set of stack traces which we've written in completely. And this orange document is some stack traces which our writer thread, our signal handler, is halfway through writing into the ring buffer. So our reader sits there, it finishes. Bear in mind we can have multiple writers, but multiple writers were OK. There was no bug in that respect. We had our reader thread, and there's only one of those, comes in, it finishes reading that document, and I had a missing barrier to stop the reader from reading a partially written set of stack traces. So this is also a classic, just following on with what Jean-Philippe has been saying earlier about trying to make sure you've got your memory barriers in the right place. This is a good example of something where my writer thread really needed to have a bit there to say, yeah, this is committed, I'm done. and only when it was genuinely done should that reader thread have followed on to get the next element in the stack frame. So that's quite a good subtle concurrency bug that would have never been spotted without open source code review.
Don't compliment yourself. It wasn't subtle.
It wasn't
Simple.
subtle. It was stupid. It was stupid and simple. Okay.
You could have done so much better.
Yeah.
We were all disappointed.
Thank you. Thank you.
Shortly afterwards, you lost your job. Just say it.
Extra credit.
Extra credit? Oh my.
Native profiling tools. Yeah. Native profiling tools.
All right.
You might speak quickly.
Okay. So we're going to have to go quickly through this, and then there's no time for your questions. Okay. So we looked at async get call trace, and we looked at get call trace, and the level at which they profile your code is at the line of code. And every line of code in Java can break down into many lines of code on the assembly. And we also noticed that it completely ignores all the native methods that you might be calling, and they don't report any of that. So some profilers have the benefit of that. We'll just go through them very quickly. And some of them allow you to profile hardware counters, which is where Sergey's going to walk in and blow our minds. Right, you have Perf, which is the Linux profiling tool, and it can be made to work with Java, even though out of the box it's not going to give you anything. So I suggest you look it up. There's some very interesting efforts going on to make Perf work with Java, and notably there's JMH integration. Who knows what JMH is? JMH, great tool. And the performance, the perf integration is a great feature for that.
When you say work with Java, we should caveat that. It does work with Java at the moment, but its feature to say where in your Java code are you actually spending time, that's the bit that doesn't work, right?
Yeah, the challenge there is that perf is for compiled ahead program, so there is a given binary it can look at when it tries to make sense of all the data it recorded, whereas Java just, we compile on the fly, and when the program is done, there's nothing left to look at. So the profile it sees can't be correlated to anything much, and it needs a bit of help there, and there's some efforts going on to make that work. Right. The Solaris Studio, which we mentioned, it's a secret weapon. No one uses it except for very few people. If you read, there's a performance book by Charlie Hunt, who's a great guy. It's this thick, and he tells you all about how he's using Solaris Studio. Read that book. Give that tool a go. It's a bit of a mystery tool, and you will have to dig up mysterious documents, and it's sort of not easy to find and work with, but it's worth a go. And then you have ZVision. ZVision works for Zing. It's not an OpenJDK profiler. It's very informative. There's no hardware counter support as opposed to, say, Solaris Studio or Perf, but it does profile on the assembly level and on the native level. I would also add it's slightly ugly, but it's because it's, let's say developed by developers for developers. So
Developer UX.
Yes, that sort of thing. And that's it.
Okay.
Now we're on to the conclusion that...
Fantastic. So, what do we cover today? What do we cover in this middle section of the deep dive session?
What did we cover?
We talked about the different biases we have in profilers. We talked about execution profilers potentially skewing the time, sampling profilers potentially have bad biases in collecting those samples. We talked about how we could use existing techniques, SIGPROF, which has been around for 30 plus years and gives us accurate timing and accurate sampling and accurate interrupts. And we talked about a bunch of the alternative profiling approaches, so PERF, which Sergey's going to talk about later, instruction level profiling. Fantastic. But more importantly, we have a kind of broader message, which is don't just blindly trust that your profiler works, and that applies to any measurement tool. Try and prod it, poke around with it, see how it interacts with your application, see what it does. We put a few of those sample things on there. Maybe run your profiler over those samples, see whether they get the safe point bias right, things like that. And also that it's not necessarily a case of some tools are perfect and always work and some don't, but you can use different tools for collecting different kind of information around your application. Yes, so test your measuring instruments. The other thing, I guess, which is really nice is a lot of this stuff is really open source under the hood. The implementation of that at async get call trace and OpenJDK is open source. Once profile is open source. The OS code for many OSs that calls those handlers is open source. This enables much better review of measurement tools and lets you see what's actually going on and what biases they really have.
There's also been, I think, credit where credit is due. There's been a lot of contributions into Honest Profiler, and there's some extra reporting tools built on top of it. It's, you know, I think open source enables a lot of collaboration, and you know, you guys are welcome to join the party. Also, just a note on Java Mission Control, which is a great profiler. If you use it in production, Oracle will come and take your firstborn. Roughly, that's the licensing model, if I understand the fine print correctly. So it's
I'm not
expensive.
a lawyer, but they will take your firstborn.
Not sure. It's something along those lines. So I think it's great that we have an open source alternative that people can use for free and build tooling for that the community needs. So have a go and see what happens.
Fantastic. And if you want more information, that's Nitzan on Twitter and his blog. This is me, my blog, training courses that I run, and that's a book I've also written as well. So we probably don't have time for questions.
I think you know, Sergey showed no respect for our time. He was late. I think we can
okay. If there's one or two questions that people have, we can take them. Kirk.
Does the skid really matter?
Does it matter? I think you need to realize what the accuracy of your tools, you know, is. It can matter for looking at particular profiles. Something typical that would happen is you would have something expensive like a lock instruction, and that wouldn't be hot. The instruction that's, you know, either right after it or 3 instructions down would be hot in the profile. And you need to look back a few instructions and say, this is what really happened. You would have a compare, and the compare would take all the cost, and the load that you're comparing to, that's a few instructions back, is where the actual cost is. So is it crippling your ability to profile code? No. But is it something you will encounter profiling code? If you profile on the instruction level, definitely. Anybody else? All right, thank you very much.
Cool, thanks. Perfect.
Just believe yourself to the love that's holding you. Touch the sun in you, your eyes are in paradise. Feet is so right, 'cause your eyes are in paradise.
So, hi everybody. I'm sorry I'm a little bit late for the beginning of that session. My name is Sergey Koksenko. I am from Oracle. I am from Java performance team. So we are working on Java performance. We are working on Java C performance. We are working on different levels, on class libraries, compilers, virtual machine, garbage collector, and etc., etc., etc. And what I'm going to tell here is just to show that there is such things like a hardware support for performance analysis. It's a widely used thing. It exists everywhere on each CPU which I'm using right now. But if you people knows about that, won't give you precise advices. I just show you that there is such things and what we can do with that, with hardware counters. So I have to show that slide because of I work for Oracle. And I really love that slide because of that slide means that I may tell you the total crap, but there is nothing happen to me with that. Okay. First of all, I will start from a very simple example. You will meet some abbreviations, some words without explanation. I will try to explain it later in the presentation. So this is a code. Who knows what this code is doing? Okay, who knows how to write a matrix multiplication? Please raise your hand. It's a simple, straightforward matrix multiplication. The question is number 2. Who ever sometimes used matrix multiplication in your real production code? Afraid that, guys. Why I'm choosing matrix multiplication for an example? It's a rarely used example. It's quite interesting. And it's very dangerous to show practical examples in presentation. Because of our industry is changing so quick that I'm showing something right now, and in several years it changed. But if I show it on a presentation, it's create an urban legend and people start to copying that. That is why unpractical example is the best way to show things about performance. So, the problem is the following. I found my hot method. Using profiler or something else, it's a very hot method. It's creating problems for my application, and I want to make it faster. What I'm doing? I'm going, and it's a problem. It's a cubic algorithms, straightforward multiplication. What I'm going to Google, and I'm looking for something faster. Okay, I found a slightly better algorithm, Strassen algorithm for matrix multiplication. I'm just implementing it, and I'm get numbers. Just measure it on my laptop. It's a year ago. It was the last Intel hardware. It has Haswell microarchitecture. Right now, it's not the last one, but it's quite a fresh one. So what I get here is a straightforward multiplication. Here is a Strassen multiplication. Strassen multiplication is like dividing my matrix by subblocks. So for small matrix, it doesn't give you any kind of boost. And here is the difference. You can see there is size of matrix. Here for size of 8K elements, I need 33 minutes to do matrix multiplication in straightforward way. And with the Strassen multiplication, I got only 6 minutes or 5. Doesn't matter, but it's much faster. It's almost 10 times faster, and even in that case, you can see the difference is quite well. So, okay, I did a performance optimization, I improved my application. I can forget about that, but let's do something else. Let's try to analyze what happens inside my matrix multiplication. I am executing tool. I will mention that tools later, and looking into hardware counters, what are happening from hardware performance point of view inside my CPU. Here is the data information about the whole multiplication, like I spent this amount of clock cycles, it was such amount of instructions were executed, L1 that loads data from L1 cache, amount of misses, stores, and blah, 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 blah. It's information for particular size of matrix. I do some arithmetic, and I normalize these details per iteration. And I see that for the single, the most deepest loop execution, I have 4 loads inside that loop, and 2 of them is a cache miss. And I know that it would be a problem. I'm executing another tool, Oracle Studio Performance Analyzer, which I will advertise in later, which can show me, which can point to me where is L1 and cache misses happens. And I found that both cache misses are happening here. I have a quiz mainly for Nitsan, Richard, and Kirk. Why I have 2 cache misses here? Not 1, but 2. It's a quiz, and we'll discuss it later after presentation. I'm explaining, but it's a very tricky question. But it doesn't matter. The problem here in that code that the most inner loop is changing my indexes and changing even my arrays, and that is why on each iteration I missed data and missed data inside cache. The most straightforward idea how improved is just to change these loops into order. Because of J, it's my last index. It will be cache friendly. And nothing happens here. And here is also the loop of J. This code, after just swapping loops, it's look like this. It's a new code with IKG. The classical implementation would be called IJK. It's IKG. What I get here? I have a cache-friendly load data here. I even move matrix A loading out of the most inner loop. I have increased amount of reading data here. In that code, I just do it in local variable and the store whole data here. And I increased amount of load and stores here. Maybe it would be not so efficient as I'm expecting, but it also comes cache friendly because of it's arranged with the most loop. Just measure. It's quite simple results. And I see that my new multiplication outperforms algorithmic Strassen multiplication. It gives me better results. Of course, somewhere here, with increasing size of metric, Strassen will outperform my multiplication. It's because of when I'm thinking in terms of algorithmic complexity using big O. And if I'm doing some kind of microarchitecture optimization, I just improved my constants, which were eaten by O, by big O. And of course, somewhere the beta algorithms will win. But even for 60K matrix, 16K by 60, I required 1 gigabytes of data for one matrix. And I don't want to measure it because of I don't know how much time it required. Even 33 minutes for 8K by 8K matrix. So here I got a very well results. I would perform better than Strassen. I significantly better in that cases in comparison with the original algorithm, with Strassen, and etc. And Strassen matrix multiplication algorithm doesn't depend from a basic multiplication. So I can do Strassen over this. So I could combine these two optimization. And in that case, I got these results. 73 seconds against 2,500 seconds for matrix multiplication. It's what I got using the knowledge about hardware, about details, about pointing. And I execute some another data and collect some things, and just to check, to compare what is happening here. So as I saw here, we get 4 loads inside inner loop, 2 cache misses. What happens here? I got a quite small amount of loads, and even 0.1 miss. I don't know how it would be happen. We'll look at that. Also, if I had concern about increasing amount of stores, and I see that the amount of stores will increased. It's okay, but amount of miss will decreased. It's a win. Anyway, it's a win. And just back to amount of loads. It's originally its numbers looks like suspicious. What is happening here? I'm just looking into assembly code, and I see that if I create a cache-friendly code where indexes pass through the memory for subsequently, the hotspot is doing vectorization. It's an unrolled loop, it's a C instruction, and one load for a bunch of data. Fine. It's a good thing. If we want to talk about hardware counters, hardware details, we should understand where we have to use such knowledge. Hardware counters is not a silver bullet. It's a place which is useful only in particular thing, in particular cases. And that is why I'm very shortly and very quickly run through the performance analysis methodology and will show the place for hardware counters here. So the key idea of performance analysis methodology is to understand in this following order what is the problem in my application, where the problem is located, and where to sync it. Usually, the whole previous session about profilers is a question of to answer where, but without the answering the question what is the problem. So it's a general direction, just in that order. And the second thing in performance analysis is a top-down approach. We should look into large problems, large things to understand what happened on system level, on JVM, application, later on microarchitecture. Because of, if you have a networking problems, it doesn't matter with your hot code, it doesn't matter what are you going with microarchitecture things. You even don't see that problems without fixing it on a higher level. And the fixing problem on the highest level give you much higher benefits than lower level. During a lot of presentation which me, my colleagues did in different places, we created some kind of mind map how to deal to the same goal. Kirk and my colleague Alexei showed it on Devoxx Belgium. And it's like short path for different ways to switches how to do it. It's completely invisible on that screen. That is why I'm showing you a link for that. Okay, so how we are going? We are start doing system monitoring. We are looking from the top down. Do we have a lot of system time now? Yes, we are doing one thing. No, looking later. What happens with our interrupts and etc. If we have a problems here, it's not one way. Other way, we are continue our exploration. Do we have a lot of I/O? With I/O one way, no I/O, continue exploration. Do we have a lot of idle time? With idle time, there is one bunch of things we have to do. Okay, so finally, pass through our explanation, we came to the station when we have a lot of user CPU code. And it's the only way where hardware counters may be useful, as the ordinary usual classical profilers. Because of if you don't have a high CPU utilization, you don't get any benefits from hardware counters, from profiling, and from etc. You shouldn't execute profilers before that. So let's continue. Let's a little bit talk about CPU utilization. What does it mean, 100% CPU utilization? Who could explain me? Try to guess. It means only that there is a lot of something to do in your operating system on your execution task. Nothing more. And original classic traditional profiler just will show you where are you spending your time, but not a why. That is why the hardware counters were invented initially. Okay, what do I have? If you have inefficient algorithms, very bad algorithms like bubble sort versus quick sort, what we have? We have 100% CPU utilization. If you have problems with CPU pipeline stalls, data loading, synchronizations, like some other thing, bus locking, etc., everything happens showing is like 100% CPU utilization. For example, my CPU is able to wait the loading data from memory for 100 cycles. And really, CPU may be stalled, and CPU may be doing nothing at that time when CPU is waiting the data from a memory, like here. But from top-level monitoring tools, it's shown as a 100% CPU utilization. It's hidden inside CPU. That is why We need something to discover, to open the engine of my car and understand what happened inside. Like just a little bit of an analogy. Like our goal is to move our car with some loads from point A to point B. And there are different conditions on that. If I'm going through city center, I'm stalking on crosses, it's like a synchronization. I may be caught by police, it may be like kernel call. I may visit service to clean my ashtrays, it's garbage collector. But if I'm on a highway, I'm pushing my accelerator pedal, and my car is not able to move forward fast enough. That is why I need to do something to understand what happened inside my engine. That is why I need that things. What is hardware counters? It's quite a simple thing. It's a part of CPU. It's a hardware block built in inside your CPU for CPU profiling. It profiles CPU. That profiles cost nothing from terms of execution of your application because of its different virus inside your CPU. Of course, some processing of that data is cost you some details, but it's really completely fine, non-intrusive profiler. It's profile your CPU. How it's profile? It's profile is quite simple. It's just collect different performance events. I think, from my point of view, there is some confusing people because of all we are talking about hardware counters. But what's counter? It's just dedicated special register inside CPU. We can read it by some tools. And the most interesting is which kind of events that counters could collect. So we should talk about performance monitoring events, which are collected by these hardware counters. And here we should read some details. It's just 2 pages from Intel documentation about hardware counters. It's nightmare, different complex abbreviation, blah, blah, blah. It's just 32 pages, and etc. What's problems here? First of all, we have a lot of such events, like hundreds of events. Like there is such guys, Professor Leventhal from Intel. It was at Intel at that time. And I was on one of his presentations when he was presenting Intel Nighilium microarchitecture 2005. And he came, guys, I have 2 good news for you. First of all, we increased the amount of events, performance monitoring events from 200 to 900. But now we can collect and do a lot of measurement information. It's required understanding how microarchitecture works. These events are platform dependent. Intel events are different than AMD events and ARM events, and etc. Even Intel changing the events from one CPU to another, etc. Other things. But in general, I want to say that the core performance monitoring events quite similar. They're quite simple. The core microarchitecture principles of all modern CPU are the same. Cache miss is a cache miss on Intel, on AMD, on ARM. It's the same. It may cause difference, but it's the same issues, the same problems, the same data organization, and etc. So, how to work with counters? Counters, they're working in 2 modes, counting mode and sampling mode. Counting mode, it just helps you to collect the whole numbers after execution of your application, just to tell me how much L1 cache misses happens during execution of my application. It's a way to create a monitoring tools to collect statistics. And all counters are able to work in so-called sampling mode. There is a sampling threshold, and when I collected enough amount of events, I just do an interrupt, and corresponding tool may find the place where this interrupt happens, and this mode allows to create a profiling tools for that, like counting and profiling. And another little bit problem, as I told you, that counters is just registers, and we have only few amount of registers. On Intel, it usually 3 fixed registers which collect only particular dedicated events, and 4 programmable which could be changed, and really more than 900 events. What does it mean? It means that in some cases I should do multiplexing. Of course, it should be performed by tool, and tool should execute your application for a long period of time. And here, tool is collecting this counter, here is collect this, here collect this, to generalize the statistic finally. But it means that the whole period of execution, the application should be in steady state. It behaves the same. If we change behavior of our application in time, we collect wrong statistics. For example, the most famous probably hardware counters tool like perf-event, it's able to do multiplexing. Some tools are not able to do multiplexing, it's just problems of the developers, something else. In that case, I have to do multi-execution, multi-running. I have to execute my application, collect these counters, execute it again, collect these counters. And it's again create me a problem that from run to run, it should behave the same. Correlation, like Oracle Studio Performance Analyzer, it's not able to perform a multiplexing. It's boring, I have to do some kind of multi-running here. I just to put my counters of my interest into command line, execute it. Oracle Studio Analyzer get, oh, I can do it, it's conflict, I don't have enough register, I have to switch these things manually. And 2 general issues with hardware counters is instruction skid. Sometimes a counters not precise. Really, it's not an issue. If you know which counter are you looking, you know that it's shown you for that instruction, but you may go up on some instruction and find the real instruction who did it. It's not an issue. It's doing with some experience quite fast, but the real problem is so-called uncore events. For example, we have this single large L3 cache for a lot of cores, shared between cores. And L3 cache also produce performance event like cache miss. But which core is the source of that event? It's also a problem. That is why we are looking. We really prefer to deal with homogeneous applications. Like we are creating micro benchmark to execute the same code on all cores, and it doesn't matter what is the source. Somewhere, use your mind in that case. Just general advice. Typical usages of hardware cases. It was created for hardware validation, first of all, and performance analysis. Hardware counters were invented a long time ago, but the first production CPU, it was a Pentium with the hardware counters. And particular usages. And through the time, people found and created a lot of different use cases for that case, like JRocket. Who knows about JRocket? Who remembers that? JRocket used hardware counters for runtime profiling and code recompilation, for better code recompilation. There are a lot of tools who are doing a test code coverage for using hardware counters. More interesting for me, I didn't heard about that, but I read some articles about that. A lot of guys right now are using hardware counters for software attacks and software defense. For software attacks, if you have a profile of encoding application, and you may exclude some branches, if you know algorithms, and you know hardware counters for that algorithms, you may significantly reduce brute force space. It's a problem. That is why usually the hardware counters require root access for works in a lot of cases. And software defense is like a different situation. You're making collect statistic of your application, extract like a behavioral signature of your application, and if signature of your application is changed, it means that your application will injected. Like it's different areas. What I'm using is performance analysis. About tools. Here are 3 tools which I am using in my job. First of all, of course, it's Oracle Solaris Studio Performance Analyzer. It's really a bad name, but I even don't work on Solaris. The Linux version is enough for me. Also, I heard some rumors about a Windows port, but I never seen that. So it's probably something like this. The second tool is a perf, but as they wrote, the perf is a bad name for Googling, so they usually called it perf underscore events for Google things. It's a quite powerful tool which do all things like monitoring and profiling, but perf has some lack interaction with Java. It's fine interpret with native code, and even the Twitter guys did some improvements here, but it's no open source. Oracle Performance Analyzer pretty well works with Java, and it's able to bind hardware counters to your Java code. It's the only tool at the moment, as I know, which is working here. And of course, our micro-benchmarker tool GMH, which have a lot of integration with perf, and etc. Of course, there are a lot of different tools which working with hardware counters. Mainly, it's a vendor tools, and there are a lot of other. I will send you. And just to show, it's a perf events and a list of the key events from perf events. Like this event, it's count amount of clock cycles. This count instructions, cache reference, branch misses, data translation and buffer, L1 cache, and etc. Quite similar, quite simple. And here is how Oracle Studio changed the name. The only name which is the same in both cases is the amount of clock cycles. Here is the same event as the instructions. Here instructions. Here is 2 most interesting event, and etc. etc. Just for example. Okay. What usually we are doing with our hardware performance data? So execution time, it's like amount of clock cycles divided by frequency. I don't want to talk about frequency. Frequency is not our side, it's hardware optimization. They are increasing frequency. Our goal is reduce cycle count. How we are doing to consider it? We execute application, collect hardware counters, and all hardware counters counts use such things like pass length and CPI. The really pass length is the amount of instructions, I mean assembly instructions, because of the executed in CPU, and the CPI is the cycles per instruction, the average amount of cycles which are spent on instruction. Different tools, some tools work with CPI, some tools work with reciprocal value like IPC instruction per clock. Cycles per instruction, instruction per clock, it doesn't matter which I'm working with, I will show both of them. I've seen frequently that, for example, if deal with hardware, Intel guys love CPI, AMD guys love IPC. I don't know why. So, as I told, our goal is reduce amount of cycles. It means that I have to reduce this multiplication, pass length, and CPI. Typically, in my history, to find an optimization which reduce pass length and CPI is very hard. It happens. It's possible in some cases, but it happens rarely. It's like a gold case when you reduce pass length and CPI, I got much smaller application. Usually, when I'm doing some optimization, I improve Java code or native code or compiler. In some cases, I reduce pass length by increase CPI, and my goal is just a multiplication of the same all over. It's my goal of my optimization. In other cases, I'm increasing pass length and decreasing CPI. It's more typical cases and our goal. So pass length, its relationship to algorithmic complexity. Then more efficient algorithms I'm using, then less instruction I have to do. And CPI is the efficiency of utilization CPU of hardware inside my CPU. This is particular numbers for today's microarchitecture. don't know what will happen in a couple years. But if you are seeing the 4 clocks per instruction, it's really bad CPI. It's nowadays. The CPI 0.2 is the ideal. It's the theoretical limit for Intel hardware to perform 5 instructions per 1 clock. I never seen application which are able to do that, but it's theoretical limit. Usually, the question about 1 it depends which hardware are you using. But like for Nehalem, it's a fine number. For Sandy Bridge and etc., it's not a real good number. It's like a bad number. But Nehalem, it's 10 years older microarchitecture, so you should look into something new. What we are doing, I'm just collect statistic, monitoring, and look into CPI. If I have a quite low CPI, I shouldn't drill into CPU behavior, what happens inside. I just want to think how to reduce path length, how to do less instructions. It's the first goal. But if I have a high CPI, I have to understand what causes my high CPI. What's the reason, like memory stall, branch stalls, instruction dependency. And depending on the problems, I should do the corresponding action. As I show you in my first example, I found that we got a lot of memory stalls. I don't tune data structures, but I have to add here, tune data structures or tune data access patterns. I changed data access pattern, and I became much more memory friendly, and I improved the behavior. Particularly, there are a lot of different classifications about inside CPU issues. I'll show you several of them. The memory-bound classifications cover this list of events like TLB misses, caches, NUMA access, memory bandwidth, etc. It's the most area where Java applications suffer from CPU performance, the memory. It's the main problems, and here there are a lot of things which we are looking for. Sometimes we have to work with a CPU-bound application, like we call it core-bound. When from hardware point of view, the core execution engine is our bottleneck, like for long latent separation, floating points, bad speculation, and etc. If you're using hardware, for example, like which is 2 years old or later, not Haswell, but Sandy Bridge, F-Bridge, Nehalem microarchitecture, you will have, for example, a lot of problems if you are doing floating point arithmetic with denormal numbers. Because in that case, they are not performed on hardware efficiently and require a lot of problems, 10, 20 times slower than usual multiplication. Starting from a Haswell, Intel fix that problems. But this event, looking into FPS floating point assist, may pinpoint you the problems where this bad floating point arithmetic happens, for example. And another case which is really hard to solve for on Java level, usually we have such problems on JVM level to change it like instruction TLB misses, instruction cache misses, like branch misprediction and all other things. For example, several months ago in JDK9 trunk, we did such optimization which called segmented code cache. We heard about that. We have tired compilation with C1 and C2 compiler, and in old scheme we are putting the all compiled method in just subsequently in the same place. It leads that C1 compiled methods which have a short period of life, they split my C2 compiled method. We have a large period of time, and it creates a lot of problem for instruction TLB cache miss. Just to create two spaces, if we have big chunk of memory for compiled code, we split it half. Here is we are putting C2 compiled method. Here is we are allocating C1. It creates the whole places here. It's really fine things. Okay, it's all that I'm generally wanted to talk about hardware counters, but I want to show more examples.
Can you comment on the role of idle in all of this?
What?
Types of idle?
Idle? What do you mean of idle?
Idle? Well, idle time.
I don't work with the hardware counters. I have problems with idle times.
Okay. Never mind.
I have to have a high CPU load because of in case idle time the CPU just slept.
Okay. Never mind.
Okay, just the second example. I'm executing a large standard Java benchmark. These benchmarks, it's a nightmare. A lot of Java performance engineers from a lot of companies, and some of us even have nightmares with that. It's simple execution of perf. Call me statistic for execution. That like this clock, there is clock cycles, instructions, there is time cycles, branches, blah blah blah. A lot of numbers, like some commas, and even the perf count IPC for me, instruction per cycle. Not CPI, but IPC, but it's really not good to look into that. I did some extraction from that, just manually took the normal values. What I could see from this benchmark and from this instruction, I see that my IPC is a bad. I'm execute really only one instruction per 2 clock cycle. I know that for modern architectures is not a good. So this amount of cycles, this amount of instructions, have such amount of loads, and etc. etc. How to find the problem here? The first idea. Because of the magnitude of values is the same here, it's look like, I may guess that the problem is here, it's a potential issue. I have a lot of data loads, I have a lot of L1 misses, and I have quite a lot of L2 misses. Let's perform some magic calculations. I know, and you may know, it is simple, just Google it or read documentation, that 4 clocks is the cost of L1 cache load. So I just multiply it. My 338 billions of loads to 4 clocks. Just cost. 36 clocks is the cost of L3 load. LLC, it's last level cache. It's equivalent for L3. It's the cost of my L3 load. I have no data for L2 by default using perf, but I may guess that here is the L1 misses and here is L3 loads. So the difference between them, they should hit on L2. It's my guessing. So 12 is the cost of L2 loads. It's amount of clocks. So I just do calculation, and I want to understand how much I spent for waiting for loading data. But in reality, just compare these two numbers. 2,400 versus 2,200 cycles for the whole application. How it would happen? Maybe I did something wrong in my computations. How I realized that the amount of clock cycles required for data loading into registers, loading from caches into registers, larger than the amount of cycles for my whole application. Who may guess? It's superscalar architecture designed to solve such problems. All these latencies, these 4 clocks waiting, these 36 clocks waiting, they overlaps. All that loading overlaps. So in reality, my waiting data doesn't wait so much time. I'm not waiting so amount of time as I calculated. And I don't know how much I'm waiting. I could guess that it is a problem. It's quite, even it shrink, even these 2,400 clocks are shrinked into real value in parallel, it should be really a big number. But what I'm doing here, I'm seeing Here's the different problem. Oh, Kirk, do you know? Yes. The smallest number here is the biggest problem here. I'll explain you it, and I will show you if you are working with a memory-intensive application, the first thing which you have to look is a DTLB misses. What is TLB? It's translation. It's a special part of CPU which are translating virtual addresses into real addresses of your physical memory for data loading. If your CPU executes instructions related with some address calculation, it requires access to TLB. So TLB, it's a small cache inside CPU. It's really small because of it should be fast. We can't wait that small cache for address translation. It really can't be increased. If you want to increase this cache by hardware, we'll decrease the speed and we'll get a lot of problems. And if our data inside the TLB means for translation, it's fine, it's okay. But if we don't find requirement for our data address translation inside TLB miss, we are got it in our TLB. We are getting a TLB miss. It may cost 100 cycles, but we have a particular counters which can help us, like the TLB load misses work duration. These counters may show you how much time you spent in TLB miss work. Just collect it, and I see that I spent 13% of my time of executing that application, these cycles and these cycles, only just loading new information into TLB. Just it's a huge amount of time which I spent on TLB misses, but it's only part of the story. Okay, 13% of time, someone may tell you that it's not a big value. I want to do 5x time optimization. But if there is no information about your address in TLB, you get a problem. These loads can be cached, they can be predicted, it can be prefetched. So it's create a load delays which which spread through your application. And what to do with TLB misses? There are two ways. First of all, try to use less data, shrink your data somewhere. Use your mind, or use large pages. It's a special command line for Java. It's very easy. You can easily Google how to enable it for use in all kinds of operating system. So I'm just turned on large pages, and I got 20% boost of my application. I did nothing, really. I wasn't looking into my code. I wasn't executing profilers. I don't know where the problem located. It doesn't matter for me because of this general issue. I just add one command line option, and on different operating system, I have to do some different things for enabling large pages on huge pages on the Linux. And I got 20% boost. It's fine. My IPC increased. It's better. Just to compare to understand what happened here. The amount of clock cycles is the same because I measured it for the same period of time. Because of my application is working fast, I was able to perform the large amount of instruction. And my DTLB works duration, the spend time, reduced significantly. It was reduced more than 10 times. What was my goal? It's the key benefits. The cache misses remains the same. It looks like it's a limitation of our hardware. This amount of loads. And just to compare, to understand what happened in here, it's the same data but normalized per transaction. How much things are happening inside the single transaction of that benchmark. Here I have the same amount of instructions. It's okay, I didn't change it. I need this amount of instruction and this in both cases for doing the same transaction. I have the same amount of cache loads because of just simple instructions which I have from that set. I required less cycles. I got less cache misses on both levels. And the TLB, just careful, load data from cache, and TLB is the similar numbers. So it used really frequently. So it's all about that example, and the third real tricky example maybe, which will be interesting for other guys who are working with like things like fault sharing. I realized that on the last couples year, probably it started from Disruptor and Elmac's presentation. A lot of people love to talk about fault sharing. Also, the ordinary people rarely have to deal with that. So I will follow the trend. I will talk about fault sharing. It's a simple situation. I have two fields and I have two threads. It's GMH annotation from our micro benchmark harness, and I'm increasing it. There are a lot of explanations of what fault sharing is, but the problem is that if these fields are located in the same cache lines, my two threads have problems. Because of these thread lines should transfer, and etc., etc. I won't explain the real situation about that. I will show you what is happening on a hardware point of view here. But if I'm doing with fault sharing, I have to understand where I'm executing my two threads. But I may execute my two threads on different sockets, on different physical packages. It's one situation. In that case, there is nothing shared between this execution thread. I may execute my two threads on different cores inside one single package, inside a single socket. In that case, they have shared L3 cache. Different situation. And on Intel hardware, I may execute two threads on hyperthreading when even L1 is shared between two hyperthreads because of its virtual threads on the same core. And here is some data. It's an average time, nanoseconds per increment, and here's data in case of shared case, and this is improvements which I got, which I moved my fields out of the same cache line. I can do it by padding inside the data structure, just put useless fields, or we did a new annotation contending to deal with such problems in Java. It doesn't matter. So, of course, as we see, the cost of fault sharing is different. Like, it's 10 nanosecond years we are working on inside the same package, and it's almost twice times higher if we execute on different cores. I didn't have such like a huge machine because of I had only 2 socket machines for that experiment. But if I'll take something like 16 sockets, 16 multiprocessor machine, when there is no connection between some CPUs, between some physical sockets, they should pass through another. In that case, the numbers would be much, much, much higher. But if I eliminate fault sharing, I got the pretty nice number. Here, there is no difference here because of no correlation. For hyperthreading is expected. The situation because of these 2 threads should execute it on the same core and share executing resources. Okay. Let's try to understand what is happening in case of fault sharing using hardware counters. What I did, I just execute this shared case and normal case without fault sharing and try to compare hardware counters. And I understand that there is no way to do that. Too much numbers, and it's very hard to find a similarity. Okay, let's split it. Let's consider different situations like hyperthreading case, diff cores, diff sockets, and etc. The problem with hyperthreading doesn't relate it to cache line. Really. It's a completely different situation. So how our CPU is working? CPU is not able to take data from register and put it into L1 cache immediately. It requires some time for that. But we don't want to wait it. We want to continue our execution in CPU. That's why there is some buffer, write buffer, which is called. And the instruction to load data in memory put my value into write buffer. It's passed through buffer. After some time, it puts into cache. Cache it moves its later caches to do correlation with other cores, and finally it caches to memory. But what happens if my CPU did an instruction for writing to memory, and the following instruction is load from memory? It's a super scalar microarchitecture for all modern CPUs, even in your phones. I want to do it in parallel and efficient, so I want to bypass if I performed this write operation. But the physical writing in the memory is not performed yet. It will be performed some later, somewhere, I don't know when. But I want to execute load at that moment. So there is a block which called address disambiguator inside the CPU. And it's some hardware magic which thinks that try to predict if address of that load is different from address of that write. So I am able to execute that load in parallel before that write. And anyway, unfortunately, if two different threads in case of hyperthreading are writing into the same cache line, writing and reading from the same cache line, this hardware block of disambiguation is failed. The disambiguator is not able to provide information that it's different addresses, and moreover, it's clear just the whole execution pipeline. It's called machine clear for memory ordering event. So that particular event which show us problems with fault sharing in case of hyperthreading. And it's proved we have a large amount of these events in case of fault sharing on the same core, and we can see that event later. In general, I'm sure that in some cases, if you're fighting or trying to catch something specific, you should to dig into hardware details and understand what happens. Here, I have another advice for you. If you are trying to catch a fault sharing, if you have some suspicions or some ideas that you have fault sharing, and you are going to execution to that, but it's hard to predict, it's hard to adjust your threads to particular cores, just turn off hyperthreading on your machines. Just gun it away, and anyway, you will have ability to catch fault sharing just on different cores, but you won't have problems with differentiation here. Moreover, each virtual core inside Intel CPU has different set of hardware registers. It's all registers dedicated to logical core. And if you turn off hyperthreading, these hardware counters are increased here. They may be used by the first core, which is still working. It increased the amount of available hardware counter registers. That's fine. Okay. And the second situation, what we are doing in case of not hyperthreading, but different core or different sockets. Here we should try to catch such event like RFO. We should understand how frequently read for ownership is performed for our caches. Because of if I want to write something into cache line, on a cache level, this cache have to get the ownership of this line, the get of RFO operation. Here's breakdown of that operation, and here is the real problems, like amount of store mixes. And so if you're working with fault sharing, try to find the read for ownership events, and they will show if there is a problem really in that case. And just equations in compare diff cores and diff socket case. Why we have for cores on the same die, on the same crystal, we have much more events than in cores of different sockets. But as we know by measurement, the performance here is much worse than here. Or here is faster than here. Just you have to understand that there is a performance event which is just event. We just count an event, but we don't know the cost of event. the cost of that event is different. But there is a particular event which may show you, is it really a problem? Like, for example, I have suspicions for false sharing. I code my RFO events, but is it really a problem for my application or not? Okay, I'll just try to collect this kind of event, blah, blah, blah. It exists. It can show me amount of cycles which I spent in waiting my read for ownership request. And see that and here I can see that in case of different sockets, it's much higher number. And just to compare, I'm executing for 46,000 cycles here, and 29, almost 30,000 cycles. I'm just was waiting read for ownership. I was doing nothing, but I could, in real application, I could just collect this event and understand is the false sharing is a problem for my application, just to compare with the whole amount of cycles. And that's all from me. Just the general idea to working with performance, that you have to know everything. You have to know how it works, your application from up to your hardware. Without knowledge of that, it's really hard to deal with performance. But be careful. And a little bit of some list, like a classical book about hardware details. You could read vendor optimization. You could look this very interesting site about microarchitecture details, or you could find something new for that. Thank you.